Thank you, folks, for coming. So I'm Graham, and in a little later, I'll introduce my colleague, Gil. We're going to talk to you about how we have been using Apache Spark to look for signs of extraterrestrial intelligence. So I work at IBM in their emerging technology division, so I run a bunch of projects with institutions like CERN in Geneva or NASA or in the Mountain View right here in the Bay Area with the SETI Institute. And that's my favorite because, hey, it's looking for aliens, which is kind of cool. This is roughly how we're going to run the agenda. I'm going to speak to you first about the problem space that we are trying to tackle, why we found Spark was a great fit for that, but why it is that that problem requires an awful lot of data to get moved around efficiently from Object Store into Spark. And that's where Gil is kind of the star of the show. He cracked the code on how to do that, and he's going to tell you about that aspect of the implementation. So first off, the SETI Institute, a little bit of backgrounder, and I'll start with what the heck is IBM doing helping the SETI Institute. Why would we do such a thing? So there's a couple of things there. One is, as a company, I think it's fair to say IBM's kind of always gravitated to some of these big, tricky, monumental questions. Wading into Deep Blue, let's say, and chess and AI, or more recently, Watson and Jeopardy. And are we alone is kind of arguably one of the biggest questions of all time. So it was a good cultural fit. There was a lot of support to get into it. But secondly, there's a lot of data, and the computational demands are really tough. And so it exercises our products in a way that helps us then better serve our clients in other domains. So the starting point is the Allen Telescope Array. It cranks out an awful lot of data, so around 4.5 terabytes an hour. It's up in Northern California, and it's a phased array observatory. So those 42 dishes are linked with special timing software to simulate, in fact, multiple physical dishes at the same time. So by timing how you combine the signals from all 42, you can synthetically create kind of virtual dishes of the diameter that is the collective area of all 42 dishes. So quite a cool piece of technology. The problem they have is that it's really tough to kind of sort out what matters and what doesn't. So much data. What do you actually pay attention to? When do you hit that kind of whoa, 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 what was that kind of moment with a signal? And what is whatever? That's a satellite. That's a plane. That's radar. So we got involved in two areas. One was helping to do that, classify signals. And the other is to do what's called deep observe, where there's a specific target that they want to really stare at and just soak in the data and then dive into it. And I'm going to talk about both. And in both cases, Gil's going to lay out the data access solution that he put in place to make it all possible. Here's the rough lay of the land. There's the SETI Institute cranking out data. Some of it is multi-year archives that we use for training and DL, ML kind of stuff. Some of it is one-time massive observations. So we're talking kind of 5 terabyte binary files of raw voltage data straight off the antenna. We move that into Object Store. We take it up into the Spark environment with Staccato, which is where Gil, so that little blue arrow is the star of the show I was mentioning earlier in terms of how we do that efficiently. And we pump it all up into, and we use Jupyter notebooks to do the analysis and so on. All right, so that's the rough lay of the land. And as I said, this is what you're going to hear about later, the circled part. So here's just an example of what we've done. We actually used Keras with a 750 NVIDIA K80 cluster. So a lot of GPUs to build out a model, which we then imported back into our Spark cluster to kind of run signals through. And a lot of these visualizations, I'm not going to get into details of what you're seeing here. A little later down below, I'll show you that this is a useful way to sort of check the efficacy of what the deep learning process has determined to be kind of one of the, I guess you call it you can think of it like the PCA. But in any event, the point of all this was to see if we could get a solid classifier, which indeed we did. This is going to be a little hard for you to see, but as you mouse over these little sort of clusters of signals as they're plotted here, each dot is a different observation of a signal, and there you got a whole series of these horizontal bands you're seeing there. That's all radar. That's military radar or SFO probably. So it does a pretty solid job of really allowing you to classify these. So what that means is in runtime, a signal is detected, we shove it through the model, and it kind of lands in a, oh, I've seen one of these before zone, right? And you go, okay, whatever, that's radar. Or there you see what's probably an anomaly. You got a signal right in the middle of the band. It's very suspicious. That's perfectly in center, most likely. That's some sort of poor calibration. But, just to, don't get excited. We didn't actually see that. What you're looking at here, all of those images that you saw were called spectrograms, sometimes called waterfall plots. So the vertical axis is time, the horizontal is frequency, and the brightness of the pixel is how strong the radio signal is at that point in time at that frequency, right? So when you see a horizontal band, I said, oh, that's radar. That's because radar is a wide band signal that goes like bang, goes out as the dish circles around, right? And then you get another one across a wide range. Or vertically, you're dealing with a narrow band signal that maybe is drifting slightly with frequency if it's on an angle, right? So that's how you read these. If you saw something weird like that, that's not nature. So someone would have explicitly produced a set of signals to catch your attention and stand out from nature, which is, of course, of great interest. Anyway, getting back to the model, that would just naturally be an outlier. The model would go, I have never seen one of these before. This is sort of a serendipity machine. And that's interesting. So that's very helpful for the SETI Institute. Their current algorithms are a lot simpler running up at the Allen Telescope Array, and they're excited to have improvements like this. I said there's two kind of gigs going on with how we're using Spark and a lot of other cloud services that we brought to bear on this. So classification's one. The other is when we get into these deep observations. So you stare at a target of interest, often at a very specific moment in time, and I'll get to that in a minute. And then you grind it through some of the nastiest math I've ever seen to kind of figure out if there's wideband signals, for example, buried deep inside. So to give you a sense of why, so here, for example, we're talking about leakage and eavesdropping. So leakage is when you're looking for not a signal sent to you. It's when just everyday life is happening and electromagnetic energy is kicked off as a result, right? Even an advanced civilization that may have moved beyond radio as a way of transmitting, I know they're using quantum gravity or something we don't even understand, let's say, would still probably generate energy that just doesn't fit the normal expectations for what a planet would do versus a star. So leakage is a big deal. So we'd like to detect very, very faint pops in power from emitting from a planet. And I'll go through how exactly we went about doing that. Eavesdropping is different. That's where, again, you're tuning into something that wasn't meant for you. It's a transmission between two other celestial bodies that you happen to be in line with. So you're looking right down the bore line of the communication pipe between those two bodies. And it just blows by the the receiver, and you get a little bit of whatever flows past, and you pick up on that. That's eavesdropping. And again, there's very specific moments, like you can find stars that are separated by several light years, but angularly they're perfectly lined up. It almost looks like they're one dot. And there are lots of those that we can look at and just see if there's any transmissions going on between those. That's eavesdropping. So tricky to do. The assumption is that it's very faint, and here's Staccato circled up there as Staccato doing its thing, allowing us to retrieve all that data. And so Trappist is a recent system. I'm going to bring it up because it allowed us to do both eavesdropping and also, let me just get the animation going. It's hard because I got to look down at the screen down here. So this is the Trappist system, recently detected, big news. It was in CNN, BBC, everyone was talking about it because it's 7 planets, 7 rocky planets around one star, close by, 40 light years away, 3 of which are in the habitable zone. So that means mathematically they're at the right temperature to have water on the surface. And just to be clear, something I should have said at the outset, the SETI as a domain has kind of hit a renaissance. It's like really flourishing. Because every new scientific discovery, whether it's the Kepler observations showing us that, hey, guess what? We're not only are we not the only solar system with, in other words, a star with planets, but every star has planets. Every star has planets. It's a revelation, right? I mean, the idea of you want to Google something, just Google the Drake equation if you haven't seen it before. It's like a mathematical lineup of all the factors that indicate the probability of finding extraterrestrial intelligence. And if any one of those factors sort of drifts towards 0, it's game over. You're not going to find anything. So, for example, one of the factors is how many stars have planets? If it's tiny, you're done. There's no, right? Well, we didn't know. Turns out it's like 100%. And not only that, the next factor is, well, how many of those planets could sustain life? Turns out our solar system, at least, is soggy. Water is everywhere. Everywhere. They have concluded conclusively that there are even water worlds in terms of exoplanets, worlds that are 100% water, just based on density. It's a done deal. It's a factual thing. So that's incredible. Trappist is a very cool system because 3 of those planets could have water on the surface. And what you're seeing now on the screen is a very specific moment in time. We developed, again on Spark and using Python code, an orbital model. We worked directly with the Trappist team that was based in Belgium, built out a model to predict a precise moment when 1 or more planets, or 2 or more planets, were lined up. So the way to read that picture, it's kind of faint for you folks, I know, but straight down is Earth. Like just exactly straight down. So guess what? At a specific point in time, which happened to be 3 months ago, 3 planets lined up perfectly, like within a fraction of a second of an arc. So anything that's getting transmitted from a further planet than us to a nearer planet to us, we're right on the borderline of that. And we can listen in. And we know the good news is the Trappist team did a hell of a job. They had that orbital data down to kind of 25 seconds. They literally know the position of a given planet to within 25. So we knew exactly when to listen. So we set this thing up, did the ATA observation, put a good 2-hour buffer around that conjunction, which is what it's called. So we had kind of a baseline. That's just sort of the normal hubbub of the universe. And then we listened in super carefully at that moment. Now, that's a lot of data. It was about a 5 terabyte binary file. We had to move it up. We've been running wideband analytics called SWAC. I'll maybe get into more detail than I need, but just so you get why this took many days of clock time. Think of it this way. I'll get to this in a second. Wideband, looks like pepper sprinkled on a paper, and it's a random event. You really can't see what's what unless you know what to look for. Separating it from random noise is tough. But if you imagine taking a wideband signal printed on transparencies that you can look through, and you get 4 or 5 of them, different frequencies, different points in time, and you kind of hold it up to the light and move them all around with your fingers until suddenly, magically, this pattern pops out, because all the dots from different points in time line up. You go, whoa, that's not random, there's something there. That's what SWAC is, except for it's like 1 million transparencies getting moved around 1 million times a second, all inside Spark. And that's hard. So that was a lot of horsepower. You need a bright light, metaphorically, to shine through all those sheets of transparencies, and that's what the IBM cloud was for. So that's what we did. And we did see some unusual artifacts, nothing that went, oh my God, call the newspaper, but enough that we needed to look again, which we're doing. This is another type of observation for the leakage. What you do is you wait for the planet. Again, think about that Trappist system, right? Those planets are going to go in behind the star and be blocked from view. So what you do is you observe the system before and after that moment and during. So that the planet of interest, one of those ones in the habitable zone, you're watching it, and it goes behind the star, and any radio emission from that planet at that point is blocked from view. It's like the metaphor is a cocktail party, and someone who's talking leaves the room. And the result is the noise level in the room goes down just a tiny bit. And then that person comes back in again, and the level pops back up. That's what we're doing here. We're watching the overall flux, the overall radio energy. The planet goes behind the star, and if you see even the tiniest dip, that's interesting. Now, it's so tiny, you got to do something in Spark called data folding, where you do that observation over and over and over and over and fold the data at exactly the right time so you aggregate it. And maybe you'll see a power dip that makes you go, that doesn't make sense. There's some reason why there's radio electromagnetic energy coming off that planet. Now, maybe it has crazy, terrible lightning storms like on Jupiter, or who knows, but it needs investigation. That's what this was for. So the occultation occurred right there, and that's with a couple of data folds. We've got to do a lot more. Jury's out, right? But it's not going the other way. There's still, it's enticing enough that we're going to keep going. If you'd seen the power go up, then you're like, okay, I don't think there's anything there. But we'll see, right? So we just keep going. Okay, so by the numbers really quickly, because I'm going to get Gil to come up now. Lots of signals, a lot of data, 5 terabytes processed in about 13 hours of clock time. And the way we made all this work is Staccato. And that's why we're coming back to Earth, because Gil's going to get up here and tell you how that happened.
Yep. So I'm going to the second part of the talk. It's more technical. And I'm going to actually explain the components that were used in the background and how it was used. And as you saw, it's about Apache Spark and object store. Now, it's good to start to explain what is object store about, because not many people are familiar with it, and it's good to be on the same page. So object store is about to store objects. You store your files, your data in an object store, and it usually contains 2 parts. So it's metadata, and it's an object itself, the data itself. Now, the data is usually not modified, so you write it once and you can read it many times. Metadata you can modify as long as you want. You can create another key value pairs or remove. Yep. So object store is not a file system. I decided to show this one because I think it's most interesting. You can still have this sort of sense like a file system, so you create an object that name which contains a sort of slashes, delimiters. And so here you see a bucket, and you see an object that contains a lot of delimiters, and this sort of pseudo directories. So it allows you to work with object store and retrieve only certain paths that you're interested in. And you still don't need to create those directories like you create in file system as an object or as a directory, sorry. There are good things about object stores. So it's fault tolerant. It usually contains a lot of logic to achieve resiliency. So you put your data and it's not going to be lost. There are different techniques to achieve this. Sometimes it's replication. Sometimes it's erasure coding. There are different security models. And you can use Spark and other those big data projects to work with object stores directly. And in particular, let's go to Spark. So Spark, you already saw this slide in different variations. Spark can work with any object store, and it works good. So you can use Amazon S3 or IBM Cloud Object Storage or Azure. Now, in background, to make this happen, Spark basically reuse a couple of Hadoop components. It's just Hadoop packages that Spark needs. It's connectors that Spark reuse to access object store. And this is very common to many big data projects, but here we focus only on Spark. So if you take an example, you take a collection in Spark of 9 elements, and you parallelize it so it will be an RDD of 9 tasks. And now you just want to store it as an object in an object store. And then what I did, I just count the number of requests that got to object store. And you see a huge amount of requests, about 561 requests in total. There are a lot of gets, a lot of heads, a lot of put. Way more put than we actually wanted to store. We wanted to store 9 elements, not 26. And so you see, it's not something wrong here. So we started to understand what exactly happens in the background. And the conclusion was that actually there is nothing wrong with object store, and there is nothing wrong with those Hadoop connectors, but they are not optimized to work with object stores. And in particular, there are 2 issues that affected, that provided those huge numbers. So one of them is those connectors or those components from Hadoop. They basically contain algorithms that are not adapted for object stores. Those algorithms adapted to work with file systems. And the second one, we identified that, Spark used those connectors to work with object store, but we need to understand that those connectors basically belong to a Hadoop ecosystem, and a Hadoop ecosystem requires those connectors to support much more flows than Spark actually needs. And in particular, shell operations which are used by a Hadoop ecosystem, Spark doesn't need them, but connectors need to support them, and it affects very bad the performance, even for Spark. I'm trying to get deep into those 2 issues that I described. So those are fault tolerance algorithms. They basically, they create each file, each task will create a temporary file, then it will rename it and rename it again. Those output committers, I think there were different discussions here today and different talks about it. One of the issues there that those algorithms needs rename. Now, rename is not native object store operation. It basically copy and delete, so it's very not efficient. And this is how those algorithm works, because they need to achieve fault tolerance. So if a task in Spark will collapse or will be another task, so we need to make sure that what we want to persist is what will be persisted, and then those algorithms are used there. Shell operation, as I said, well, you have them in Hadoop, right? And you do some kind of stuff like create directories or upload objects. But this thing is actually affects very bad the code itself, just the software in those connectors. It has very bad effect on all the flows and also on the flows that Spark needs. And why it happens? It's because, well, consider this example. I mean, why shell operations are so costly? Because this is the previous example, so consider this RDD of 9 elements, and now each task will persist its data. It will first of all try to use those output committers. And you see this name, the name contains sort of directories. So when it will get to connectors, they will treat this one as a directory, and they will try to create it recursively, because this is how they work with the file system. And again, as I said, Spark doesn't need it. So based on those two observations, basically we understand that we need to do something else, to provide another connector. Now, why another connector? Because we want Spark to work as is. We don't want to modify Spark, and we want also to Spark to use all kinds of objects, so Parquet objects, for example, or CSV objects. So we don't want to modify anything in Spark on the behavior. So we decided that we need a connector that will be object store optimized. And the project that we call it Staccato. It's an open source project. It basically transparent to Spark. So Spark doesn't really know that it has something else, and Spark speaks to Staccato. Staccato exposes the same file system API as all other connectors. You don't need to modify anything in Spark, and it's not aware of it. But then Staccato internally is very optimized to work with object stores. And it knows how to, first of all, it doesn't do renames. So you write everything in one time. You don't need to rename them. And you also achieve the same fault tolerance as you expect with other connectors. And you don't need HDFS, because there are different directions in the Hadoop community, so you can use HDFS as some local store. You don't need it with Staccato. Back to the same example again, you will see that Staccato, with the same API, it will basically provide what we expect. I mean, we wanted to persist 10 elements, so we have here 11 put, because we also create some success object and another one. And we have 2 heads, and we have 1 get and 0 delete. And this is how it's supposed to work. Yeah, we still have time. So there's a little bit benchmarks just to show you that it really works, although Graham already said that they used it in production. So this is, we compare Staccato to output committer version 1 in Hadoop, and we see that Staccato is about 18 times faster for write-intensive flows. But Hadoop community is moving forward. So we have now V2 output committers. Now, V2 output committers, in a contrast to V1, it just do a lot of things in parallel. But it has another issues with speculative mode. And previously in the talk, Databricks mentioned that it also has issues that a lot of temporary files are not deleted. But still, because it's working parallel, Staccato achieved only 1.5% improvement. However, the interesting part is that if we compare the number of REST requests, then V1 and V2 committers will do the same amount of them. And Staccato here sends 21 times less requests to the object store. Now, those requests are costly because we usually pay for them. And depends on the network, they will also affect the overall performance. Oops, I'm on time. And the conclusion.
Okay, I'll come back up. So, we'll sort of conclude. We each have a different part of our. Here, I'll go to the study. A different part of our conclusion. I mean, my conclusion was that this was indeed a lesson learned. The SETI project stress tested a lot of our commercially available solutions and the ways in which we use open source, including Spark. We very quickly identified that object store to Spark connection as a serious impediment to us doing the kind of work we had to do. So the takeaway was simply at the level of a business use case or a requirement, in this case in the science domain. This was make or break. We would not be doing the analysis we were doing. We would not be achieving the results. And we wouldn't be able to say to the SETI scientists, sure, we can do that, if we hadn't solved this problem. So that's the simplest takeaway. Gil can give you a takeaway from a technical point of view.
And my conclusion is that sometimes it's people think that something wrong with object store. They are not optimized. Things are working bad with them. And the conclusion actually from this Staccato is that there is nothing wrong with object store, and there is nothing wrong with Spark. It's just a software that sits between object store and Spark. It's not well optimized to work with object store. It creates a lot of requests. It creates a lot of traffic. And Staccato was exactly another software that just knew how to resolve it.
Yep. So just before we shift into questions, I'll just tell you something kind of fun. If any of you are here because you're just not just interested in Spark, but you're interested in kind of the subject matter that this talk was about, the SETI science program. If you're local or if you're staying here over the weekend, just by coincidence, we meaning IBM and the SETI Institute, are running a hackathon at Galvanize here in San Francisco. Last I heard, there were 55 seats open, of which 51 are filled. So there's still, I think, 4 seats available if you want to register for it. I have little info sheets if any of you folks want to jump in on that. It is to set you up with the exact environment that you saw some of that cool stuff going on with. There is a very specific problem that the SETI scientists are asking people to try and help them with. That's the objective of the 2-day, weekend-long hackathon. Best ML model to crack the code on what they're going to lay out for you is the challenge. There's prizes, all kinds of stuff going on. And all of the SETI leadership are right there, including real leaders in the domain, like Jill Tarter, who is the co-founder of the SETI Institute. So she's there both days, right in the thick of it. Very, very cool event. So if you're interested, come see me afterwards. I've got a little card. Registration's open till 10 p.m. tonight. And that's it. So any questions from the audience? So there's one behind you there in the blue shirt. Yeah.
So when you said do a 5 terabyte binary file, I assume you mean lots of small files that total 5 terabytes, not an actual 5 terabyte file, right?
I apologize, a 5 terabyte binary file, what, sorry?
You said when you did the long scan, you ended up with a 5 terabyte binary file that had to be processed in Spark. So I'm asking, that's actually a bunch of little binary files, not a single homogeneous 5 terabyte blob, right?
Actually, it's 2.5 terabyte files is what we had to deal with. Now, moving it into Object Store, we had to create an SLO with a manifest of kind of 1 gig chunks to make it consumable. But in fact, the way it was handed to us by the SETI Institute is literally 2 files, 2.5 terabytes a pop. And we had to kind of deal with that. Yep.
Hi. This is a very cool project, and thank you for doing it.
Yeah, great.
I have a question. Did you evaluate how much you might be losing from not using data locality like you would with HDFS? Because presumably you don't have that benefit anymore.
Yeah, and I have to apologize because I've had each of you had to repeat. So unfortunately, I'm deaf in one ear. And so if I could ask you just to repeat yourself, but everyone else probably heard you, but I didn't. Go ahead.
I'm assuming you are losing the benefits of data locality.
Oh, I see what you mean. Yeah, that is correct. Yeah, you're spot on. So some of the data we collected, the mechanism we used is somewhat lossy because you heard me earlier say, okay, it's 4.5 terabytes per hour that's collected, yet a multi-hour observation with 2 beams, is each beam 2.5 terabytes. So you're absolutely right. There's some data loss, if that's what you're referring to, in the data that's collected. Is that what you meant?
No, I mean locality. So the data that you have in the object store.
Sorry? You want to answer? I apologize. I'm
So it
having a hard
depends.
time hearing.
So we use object store. You can have your cluster with HDFS, and then you need to scale it. And if you want to scale HDFS, you need to also scale compute. Here, the idea was that you have compute, and you have your storage separated. And if SETI will collect much more data, you just put it in an object store, which is much cheaper to keep in there. And your compute will basically remain the same, because if you want to scale both of them, it will be too much expenses. And then data locality you do lose, but then you achieve much more benefit that you can scale them separately.
Okay, apologize. There is some loss in time series data. That's what I was referring to in terms of how they compress it.
Can I have a follow-up?
Yeah.
On the problem domain, I'm curious as to how did you select this frequency band as opposed to any other observation you could, like Newton in X-ray and...
Right. So so part of that is dictated by the Allen telescope array itself. It has antennae which give you a specific frequency range. But in fact, you don't pick one frequency. That's the beauty of it, and part of the reason the data files are so huge. It's actually tens of thousands of frequencies simultaneously. The antenna construction is such that it's collecting for a good patch of the sky. It's got about almost a 2 minute square area that it could observe. And depending on how you want to manage the time series compression, it can be up to 1 million frequencies concurrently.
But you don't extend into the optical spectrum? Or
No, not so. They do optical SETI as well on the Lick Observatory right on the other side of the valley, but not at the Allen telescope array. Yeah. That's where you're looking for lasers instead of radio, but you're exactly right. Yeah.
Does anyone else have any questions? Okay. I think this may be the last one we could get in due to time.
Does Staccato support encryption at rest?
Well, encryption at rest, it doesn't have client-side encryption. It doesn't care about if you have encryption in the object store. It is support. It's not, it supports it.
Anyone else? Quick questions?
Okay.
Okay, I think that's it. Thank you, guys.
Very good. Thank you.